Hello, IK here. Welcome to OpenAI Embedding Model Case Study. Here it is for I write prompt how to grow tomatoes, generate embedding, generate embedding. Here it is, loading, and this is the result, embedding. This is what is embedding. It is a vector. Here it is with only five members. This is vector is array. Here is only with five members. It is a decimal number from 1 to -1 in that diapason. And this data we ask, by the way, in this data vector length. You see, vector length 1536. Every vector, embedding vector, there is a 1536 number. It is array with 1536 six number. Every number is a result in a neural process statistic, result of 20,000 parameters. 20,000 parameters calculate statistic in a neural network. And the result of that, we have, it is embedding vector with 1536 members, 1536 dimension, 1536 spaces. But the most understandable context, 1536 context, massive content would be tokenized. Tokenization means that every token at first massive text would cut in a chunk, and every chunk is token. All word also is token. That chunk can be all word, can be space, can be interpunction, etc. And so cutting massive text, every token go to neural, at first it is token, it is word, it must go to vocabulary. Vocabulary content 30,000 token. It is total token. It is like ABC, like letters, 27 letters in our natural language. Here is a 30,000 token, a different token. And every of that 30,000 in vocabulary file, there is a number. And tokenizer in that massive text tokenized, and every token give number, and that number go to neural networks. After that process of tokenization and in dictionary and vocabulary, and numbers go to massive text go in numbers, translated in numbers, go to neural networks. And neural networks have numbers, and trillion numbers, trillion, 2 trillion, how much there is a token in massive text. And every token go neural networks, there is a 1536 part, 1536 dimension, 1536 spacing, but the most understandable, 1536 context. and that token go in context agriculture, sport, etc. And in every context, uh, would we make statistic about complete massive text go through every spaces, every dimensions, and in every dimensions, every token would be analyzed. And the result of that statistic is 20,000 parameters, 20,000 variables. It is weighting, it is a parameter or weighting every token in that spaces. It means that 20,000 parameter, there is some number, and every of that is weighting of that token in that context. And so that analytic go through 1536 context. And every 20 parameters would be result for one token in every spaces, in every context. And that 20,000 parameter, where is finished, create one number in embedding vector. One number in embedding vector. It is only one number, and the embedding vector has 1536 number. And every token, there is 20,000 parameter for one context, but there is a 1536 context. It means in every context, there is a 20,000 parameter. 1536 multiply with the 20,000, it is total number of different parameter, or we can say it variable. It is about trillion variable, trillion parameters. And the vector embeddings is very, very information about that token in every space, in every dimension. 1536, very important number. It is vector embedding. And word embedding here is not, here is only connect with vector, embedding that vector. Embedding that vector is embedding to token number. Neural networks don't see and don't understand the word, and there is no contact with words. There is a contact only with number of that token in words, translated in vocabulary, and only numbers. But when we have one massive content translated in number, it is sentences. First token, second, after that, and point, dot, but that dot also all is in token, and all that in numbers. And of course, number, and last number means dot. It is one sentence, and that all massive content is in numbers, but that numbers create a sentence. And neural don't know what is a sentence, don't know grammar, but neural no count, no calculate statistic. And for every token, and there is a 30,000 different token, but in massive content, there is a trillions, can be trillion token, and every of that token, it means every token of 30,000, it is like letter. A letter happened. We see letter in text many times in many places, and so token in massive text, token is many times same token, incorporate in many sentences, on the beginning of sentence, on the end, in the middle, behind this token, in front of this token. All of that calculate statistic. And a result of that statistic is that embedding vector, that embedding number. And for example, if in space, in context, agriculture or garden, we can be more precise, token tomatoes, there is 0.99 in garden, but in metallurgy or in IT, there is 0.007. It means that tomatoes or tomatoes token is not often in a text, in massive text about in space of IT, metallurgy, but is very often in garden. So would be with the token potatoes also. And that statistic is only meanings of what has neural network. Neural networks, there is a statistical meanings and no other meanings, only statistical meanings. But if you that statistical meanings put in embedding vectors, and you have 20,000 parameters about in every context, that statistical, that number meanings, that meanings in machine learning. Machine learning is neural networks and embedding vectors, that two modules after tokenization. They don't need token and they learn. Process of machine learning is that process when all massive text like number after tokenization coming in neural networks, and in that moment disconnect with the tokenizer, and 1 month, 2 months, 3 months machine learning. What learning? Calculate statistic for every space, for every context, calculate statistic, save a result of that calculation for every token, save it in 20,000 parameters, and create embedding number in embedding vector number for that space, for that token. When it is one direction. Now, when we write prompt after finished machine learning, process of learning after 1, 2, 3, 4 months, machine learning is ready to be used. It is locked in that situation and ready to accept prompt. When we prompt something, that prompt is, we prompt in a word, that word must be cut in token. Who make it? Tokenizer. Tokenizer and vocabulary file. Tokenizer by vocabulary file, our prompt cut in a token word, and that token word translate in a number vocabulary. And that parameter coming through tokenized vocabulary, coming to machine learning model, coming in large language model, coming in embedding model. And every token, there is a vector, embedding vector. But in this situation, all prompt from that many vectors, all prompt will have, all prompt will have one vector. And that prompt can be document, bigger document, can be part of book, would be will have only one only one embedding vector. Who give that only one embedding vector? It give model learning, finished model learning. It gives a large language model, or not or, but embedding model. And prompt, there is can have a lot of token, but some kind of little massive content. But we'll have only one vector, and that vector we see now. This is that vector. I often said large language model with goals that I said you that LLM and embedding model, they have same fundament. They have same fundament, but large language model on the prompt give us a natural language. Result is a natural generate, LLM generate text, generate textual response in a natural language. But embedding model return, give us embedding vector. Because of that, we call that embedding model. Return us embedding vector, one embedding vector for one chunk of book, for one chunk of reports, etc. And that one vector, what we see now, this form is only that we see what we received from prompt embedding, what we received from prompt embedding. Here, you see, if I write articles, it is LLM. I ask LLM, articles loading, you see, I have all articles. But this form connect this form here connect only embedding. And embedding model give us embedding vector. And so we have name embedding model, embedding vector. For what? For chunk of text, for one part of the, how many we can put in that text 34,000, I don't know, words or letters, I forget now. You can ask. And it means that all library today, or all massive content of Google, of Amazon, uh, use embedding model to semantic search, for semantic search. What is semantic search? Semantic search is a comparison, compare prompt vector. It is a vector of a chunk of some book, one vector of part of one book. And compare embedding, give embedding give a vector, embedding vector for that chunk of, and also all database, all library, all chunk, all part. There is a oven embedding vector, and compare a prompt vector with existing in a database vector. In database vector, existing embedding for million chunk in library, or 100 million chunk in library. And comparing that to vector give us meaning search. Semantic search, it is equal meaning search. It means that, for example, if embedding vector, there is a 0.99 for tomatoes, for example, and all chunks in library database vector who have connection with garden or something about garden, maybe, and word selling, there is something about garden, we will we have, as a result, we have a comparison, and a near number is bigger meaning, bigger semantic, bigger similar to our prompt. We find something, and Google give us all other what can be interesting for us. In YouTube also use embedding for semantic search. What we see like promotion to see in list of what to watch, what give us Google, that list is formed by our watching, and embeddings or semantic meanings mean find near content what the user look at, what user watch, analyze other semantic meaning, near content, what did that user like to see, like to watch. Again, now this form only we use it for test. What give us embedding model? Embedding model for our prompt. That prompt can be a lot of text. Give us one vector. And now we will see code. and something else. And it can be some in our data, our chunks of text can be in memory of our computers. Like next example would be, or can be database with columns embedding. And one times all content in library can have that embedding, vector embedding for all library chunks and fill database give us embedding model. Embedding embedding model. Only embedding model can give us embeddings vector, one vector for every chunk. Uh, because it is a job of embedding. Embedding don't go like LLM, but stop and give a vector, give a vector for that one vector for a bigger text, bigger chunk of some book, etc. And every chunk of book in library, maybe again million row in database, 2 million row chunk. Every chunk there would be with the embedding vector. And when we put like prompt some chunk, we search for some chunk, all near content would be offered to us because from database, because comparison don't work embedding model. Embedding model give only embedding vectors for prompt and for chunk in database. But comparison work some tools cosine similarity function outside of model. It is interesting, very interesting how model AI is very narrow goals. Only embedding. LLM give us only generate text. Okay, here we see that embedding, what embedding means, why name embedding model. Embedding model give us, when we prompt something, give us a one vector, embedding vector. Front-end user interface React from this form, what we see, we click on the button, and here is called server. It is endpoint, called endpoint in server. Let's get see that endpoint in server. Here we are. This is endpoint article embedding. User prompt equal request body. Here it is object, and it exists in a request object in properties body, and this is the structured assignment from this. This is we have this object. We have this variable user prompt. Okay, and look at we declare constant embedding, and we await function generate embedding. Generate embedding is function of what is connected and connected to embedding model. And user prompt go to embedding model, and what we have back what would be returned. If all is okay, we would be returned and see on the screen this. And we see that here 0 and 5, we think that we see 5 numbers in embedding vector from 1536. No, 1536, but we see only 5, for example. Vector length, we see embedding length 1536, and preview vector, we see 5 members array with 5 members. And we see this message. It is all, if would be, or it is all. This is very, very important. We send a prompt or a chunk of text, and we see back vector. We see back embedding vector. It is a demonstration of what embedding model returned to us. Now we demonstration case study semantic search embeddings only without LLM. We don't include LLM. This previous example was only embeddings model without LLM. Now again, only embeddings model without, but now semantic search demonstration that same, I can write, say, what is difference from previous? Difference is that now would be happen semantic search. It means that not only embedding model give us a vector of prompt, but embedding model give us a vector of all our data in this, in our case, momentarily in memory. And some outside script, outside from embeddings, will compare that vector. Vector of prompt would be compared with every vector of data, of chunk of text. And we have 4 data in memory, and we have 4 comparison, and that comparison cosine similarity function give us a score vector, and that score vector, pardon, it is not vector, it is a score number. Bigger number means near meanings of that data is near to prompt, and would be rank list of similarity to prompt. Okay, search. Here it is. Ranked result, no LLM used, context 1, 2, 3, 4. I have a 4 chunk of text in my data. And here is, you see score for these tomatoes are best grown, etc., is 0.67. About that, indoor plants, you see, plants, about gardening. But here, plants, there is a 0.294, but you see, the company total sales by quarter, it is something sales by quarter, shown 0.137, and resale cards, and this complete, there is 0.006. You see, it is last position because score number is very, very small, very, very distant from number one, distance from our prompt. And here is the data and score of data. Here is the only rang list. Let's get see what we have in endpoint now. Front end call this endpoint on the server, semantic search. In this file, embedding search, we have data. My data is in RAM, in memory, memorized. It is constant sample data, and every this data is some chunk of text would have only one embedding vector, only one embedding vector. And look at, we start with empty array for embeddings, but after process of embeddings, in this this array would be full of one vector. Every of these four data would have one embedding vector. Who returned that embedding vector from this data? Return embedding model. Here it is. When it is in memory, and after process, after calling this function, generate all embeddings, would be embedding sample data. Every data, now it is four of them, would have one vector, one embedding vector. You see, in that loop for item embedding is await generate embedding. It is a function what we can see who call every text of item of our data, and every text put in model, send in model, generate embeddings. Can we look at in a moment? Generate embeddings. Generate embedding connect to OpenAI. Here it is by key, and here it is call generate embeddings, activate model, embedding model. This is embedding model, and input text. We see what would be input text, and the response would be embedding every chunk of text. There is one embedding vector because it is zero in many vectors. How many chunks, so many vectors, but response data first embedding vector. And okay, in data we'll have embedding vector after this, and we can go back. And now in memory exist this function is execute. Who called this function? Call server. You see on the beginning where we call that function. Okay, I go here in embedding search. Now, in server, we call in a server for semantic search, we call search similarity. And embedding search, search similarity prompts, we again call generate embedding, but only for a prompt. Only for prompt. Here is a query. And the new object query embeddings is only one vector for prompt. And we have a 4 vector for data in memory ready. And now you see, we call it results. Sample data. Sample data is array, and that sample data there is a method map, like every array. And that map item, every item there is ID, text, and score. And here it is a score of every data. Score calculate cousin similarity. From what? From query embedding. It is only one vector of our prompt with item embeddings. This is two parameters. What would be compare? What would be sort by would be sort from the biggest to the lowest, and here it is from big, it is descending, no from lowest number, lowest score, but from contrary, from the biggest number to lowest number, and return result. And we see that list. We see that list from biggest number to lowest. Here is interesting cousin similarity. That function would compare query embedding and every embedding of data. We can find it, it is in utilities, here it is. Here is cousin similarity. Vec A and vec B, vector A and vector B, it is cousin similarity. Cousin is cosinus, cousin, because look at on that vectors, like there is vectors, there is a angle between, but that difference, that comparison of numbers to vectors, comparison of embeddings vectors, that numbers, it is like compare angle, and the smaller angle, it is this vector is near one. Bigger angle, for example, angle 180, it is strictly contrary to vector. Okay, you can ask artificial intelligence that explain this function, and it is a very, very excellent explanation of that. But now concentrate in this process, what happened here. And back here, semantic search turn to back, return us on the screen these numbers, this rank list from biggest, descending from biggest score to lowest score. And in YouTube, Google, Amazon, etc., it is a semantic search. We will see list what is near our watching YouTube. What is near what we ask, what we prompt in Google, or what we search in Amazon.com. It is a list, it is only data, it is only our data, and this is text what is right strictly in sample data. In sample data, when we look at no server, uh, what we look at in embedding search, embedding data. You see, tomatoes are best grown in warm weather, etc., etc. It is our data. Indoor plants thrive when placed near. It is a strictly text what we have in our data, and because of that, it is searching, semantic meanings searching in library, in Google, when when we want show, present users something similar, uh, more or less similar to to video what they watch, what they like to watch. Very, very important searching, semantic search. And because of that semantic search, uh, we have embeddings, vectors, but it is not big job. It is LLM, but input is prompt, input is some text, but output is always embedding vectors, not generate text, but embeddings vectors. It is difference in return, but in fundament, it is the same uh, machine learning model. And now there is something else interesting. If we want that generate that LLM say something, some summary about this result, uh, because it is very, very interesting to 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 see a natural language say something, and sometimes we need it in YouTube and Google and Amazon. When they search, embedding search only their data. Don't ask. Don't want anything. But in some situation where we look at some content, they want summary. And in that situation, they use LLM. It means here it is, semantic search plus LLM. It means semantic search is a embedding model, and now from that embedding model, if we want some summary, we include LLM. Bigger or less summary, we include LLM. And it is retrieve augmented generation. Retrieve augmented generation. What is retrieve? This is augmented. This is augmented, retrieve augmented generation. It is text from our data. It is outside of model. Model never see text. That's like the model. There is a no in massive text. and uh, and it is retrieve augmented. It is augmented content to final locked model machine learning, to final LLM model by retrieve augmented generation. Uh, we augmented we augmented content. We library augmented content of LLM or embedding model and augmented with database content, database data in library, data in Google is augmented, retrieval augmented generation. Okay, now look at here what we I can again ask say search with LLM. What now we have here thinking when finished is search with LLM. And look at we have that context, it is same as before, but now we have a final answer for LLM, and in this summary here, to grow tomatoes, follow these steps, etc. Uh, how many oven generated text from LLM we dictate? We dictate in augmented in our instructions to together with prompt. And okay, in this text, we can say that strictly give summary about use text from augment from our text, not from open LLM massive content. Okay, now look at what here happened with LLM. Now endpoint is this one, semantic search with LLM. Semantic search with LLM. Here is endpoint. It is query, it is what we prompt, our prompt. That prompt go like a query, this prompt, search similar prompts. Search similar prompts. Here is a parameter, only one prompt. But before we have embeddings for our data, and in search similar prompts we just see before, we have cousin similarity, search similar prompts. Okay, let's see search similar prompts. Here is a search similar prompts. It is generate embedding and cousin similarity, sort, and result. It means that search similar prompts give us all final result. Final result back to server. Search similar prompts give us not final in embeddings. Embeddings data, embeddings prompt, compare that. It is similar prompts. But now we create constant object LLM prompt, and here our instructions. You are helpful assistant. The user asked. Here is a query. It is our prompt. Here are some relevant text, it is context. Based on this, answer clearly and concisely. It is very important, clearly and concisely. We can use here strictly, but clearly and concisely, it is very, very compact with what we have in data, not what LLM there is in massive open knowledge, open neural. And look at here, our instructions, our prompt, and context. Context, all that is created here. A result and context. From result variable is a result variable is a search similar prompt. But this context, it is about wrapping in configuration of text. And this is context. Use context, query, prompt and context, result of similar, but query is our prompt. And with these instructions, we have on completion, now we contact OpenAI, properties chat, completions, create. And here is model GPT, it is LLM, a model of OpenAI. And messages, role user, content, LLM prompt. This is final answer is this completion. Choice first, final complete message and content. Okay, and we see what we see. Context use result, answer final result, final answer. Here is a final answer. Final answer is completion with that our embedding solution from similar text plus LLM. And here is calling. We call that model. We can go up on the top. Yeah, it is a server. Here it is. Here it is. We call generate embedding and OpenAI from this file embeddings. You see, when a server starts, we have generate all embeddings. Only starting server, we have generate all embeddings, and they waiting with the embedding vectors. They waiting in memory. They waiting what we search. Here it is. This is calling generate all embeddings. Calling function generate all embeddings. Look at now when I refresh this and I see server. When I stop server and now again start, now the server.js, look at what happened. all four uh, uh, here it is, new terminal. And when I start now the server, for data, uh, 1, 2, 3, 4. All our data is automatically on the start of server is embeddings. Here is embeddings, only 5. This is only 5 members of one vector embeddings. All text of data is one vector, but every vector I choose only 5 members to see, not 1536. And we have that vector by vector. But Cousin will compare this one vector of every data, this one vector, this one vector, with our prompt vector. It is Cousin similarity. Compare that, and we have score. We have score. We have score and that Cousin similarity, and that outside of model function create Cousin similarity and order list from descending order list. Model only this is creation of model. It is text, our text. Embedding generating for tomatoes. Tomatoes are best grown. Embedding generated for indoor plants, etc. And here is one vector for all that text. Only one vector, not vector for every token, but vector. This is augmented, the retrieval of augmented text. The text go tokenizate, go in vocabulary, translate in a number. But in a model where we have neural network embedding vectors, they have one vector. The model created one vector for all text. And that one vector, Cousin function, compare with the prompt and give score. And after that, we have rank list. We create rank list from biggest score to lowest score. Okay, I hope that what I can say you, I don't like use complicate something complicated. It is not complicated. If you see a previous lesson about how model learning, how model work, and you see that in neural is only numbers, and embedding vectors is only numbers, and that statistic about that numbers, it is meanings of that numbers. If we know all that, it is not complicated what we see now. We see embedding model, what is some shorter version, shorter for LL, large language, and return only embeddings for our prompt and embeddings. When I said embeddings, I think on the vector, 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 vector. Word embeddings is only on embeddings vector. And the embedding model, it don't mean that model embedding embeds somewhere, but it means that that model give us embeddings, vectors of prompt and of data. And you see now that all data can go in database, MySQL, and receive embeddings in that database. I must open columns embeddings in my database, for example, articles, and I can create semantic search from that database uh, by comparing embedding of data and embeddings of prompt. It's like Google or like YouTube, etc. Okay, if you know somebody that need a video like that, say them about that. Engage, like, subscribe, write text. More as around this video, more learning for every of us. Thank you for watching this video.